Hello and welcome. My name is John Larsen, and today I want to show how to make a behavioral simulation using PlanAhead 14.7, part of the ICE package from Xilinx. I have here started up PlanAhead and loaded a project which is called Blinking LEDs. And what it does is just to blink two LEDs um, with some frequency. The frequency is created with just a counter which is counted up here, um, and then two of the bits are put onto the LEDs. So it's really basic, but I want to show here how to simulate this circuit in PlanAhead. So the first thing that we're going to do is to add a source. So we go over here and add source. We want to add or create a simulation source, so we press next. Here we can either add files, directories, or create a file. And since I don't have a file, we are creating a file. And what we really is creating is it's what we're calling a test bench. So we are maintaining our current implementation of our hardware. So that will be the counter and everything to blink the LEDs. That one is the one we want to test. That becomes the unit under test. And in order to test this unit, we need to place the unit in a test bench. And that's the file we are creating here. It's a test bench for our test. So we'll be creating a file, and we can call it blinking. Underscore test bench. We want to create as a VSTL file and local to project, so it will be maintained in the project folder structure. So we say OK and press finish. Then we are asked if we want to add any ports to our newly created module. We don't, so we remove this one, and we are just saying OK here. So now Xilinx is adding our file to our simulation. So if we go here under simulation sources and sim1, which it's automatically is calling our first simulation, you could have called it something else. It here shows our blinking LEDs, which is the same file as this. So this is the file we want to create as our unit under test, but currently it's just a source for our simulation. The same is true for the blinking LEDs test bench, which we just created. It's just put up here because there's syntax errors into it. We haven't created or put anything into it yet, so we'll open it firstly. And it looks like a standard VHDL file. There's a few things we need to do in order to make it work. So first of all, this test bench does not need any ports to the external world, so we simply remove this from the entity area. Then, as said before, this test bench is the one testing our unit under test. So our unit in this case is our blinking LEDs, which is our hardware, so to speak. So this hardware, which is handling the counter and then putting the bit values onto the LEDs, this hardware we want to test using our test bench. So you should imagine in a physical world you would take your piece of electronics and mount it into a test bench where you can power it and you can insert signals and you can measure on the outputs. That's what we're doing here. So what we want to do first is we want to have our component instantiated. And the first thing to do is to, on here under architecture, to put in a section similar to this. So I'm cheating a little bit by having written it beforehand, but it makes it a little bit more less tedious for you to look at. So I'm copying in this component area. So what's happening here. So we are instantiating a component which is our blinking LEDs. So this is a link, so to speak, or an instantiation of our file here. So as you can see, these ports, or these ports are the exact same that I'm putting in here. That is one of the things. Then we want to have we want some internal signals on our test bench. We want something to connect these two, and those signals will just be putting them in down here, right under our component, like this. So we now have some internal signals on our test bench, a clock signal, LED1 and LED2. I'm naming these signals with the same names as the connections that comes from our hardware, so our blinking LEDs, and simply because it makes it easier to work with, since you don't have to think of whether it's an internal or external signal from the test bench. So the last thing we want to do is to create the connection between the test bench and our unit under test. So this, if you were doing this in a physical implementation, would be the same as running wires from your component onto your signals on your test bench. And here you're taking the external signals and linking them to the internal signals on your test bench. So right now, if we're saving this and just using Control S for saving, you would see Xilinx recognize what I put in here and reorganizing things over here. So now my test bench, my blinking LED test bench, is becoming the top module in this simulation, and now our blinking LEDs is the unit under test as I'm instantiating it here. And the signals in and out from our blinking LED hardware is now connected to the internal signals on our test bench. So now we have set up all the signals. Nothing interesting is happening still. If we run the simulation now, it wouldn't do anything because the most important signal of all, the clock, have not been triggered. So again, as if you were using this in a physical setup, you would of course need to add a clock if it doesn't have an internal clock. In this case, it doesn't. So you would need to add a clock signal to see how the hardware is working. And the way you're doing that is, firstly, we are going to instantiate a constant. And that constant is, well, just for making things a little bit easier if you want to play with the clock speed of your test. So I'm creating this constant external clock period, which I set to have a value of 20 nanoseconds. You might now ask, why are you able to write 20 nanoseconds? In VHDL, you cannot define time. Time is just something that happens given the laws of physics inside the FPGA. And that's where the simulation can play tricks with you, because in simulations you can set up timing. You can say that this signal, you want to have it high for a certain amount of time, or you want to insert a delay here. That's something you can do in simulation of VHDL, but you cannot do it in implementation of VHDL. But it's perfectly acceptable in the language of VHDL to use delays and use timing as part of VHDL. It is describing hardware, but of course you cannot take these delays and just implement it into your hardware. You would need to instantiate counters and handle the delays yourself. But here, using simulation, we can just say, well, this has a value of 20 nanoseconds, and we can use this afterwards. So with this value, we were also going to copy in a little process, because we want something to, we need to sort of set up some hardware that is handling our clock signal, controlling our clock signal, and then a process for doing that could look like this. So an external clock process. It will set the clock signal to 0. Then it would wait for half of this period up here. Then it would set the clock signal high, and then again it would wait for half of this period. So 10 nanoseconds each of these, creating a total period of 20 nanoseconds, giving us a duty cycle of 50%. So here you see this wait for are perfectly accepted general VHDL commands, but you could never, you can't use these for implementation VHDL. It's only when you're simulating. It's quite important to remember this. It's only for simulation. So now we have finished with our test bench. We don't have any other signals to put into the test bench because this hardware is only getting a clock and then it's running these LEDs on the output. And the output will, when the test bench is run, will automatically be displayed in time. You will see that in a few seconds. So now what we are going to do is to run behavioral simulation over here. And if I'm lucky and haven't made any mistakes, it will just compile and start up the simulation. Oh yeah, first you have to define which simulation top module you're going to use. So you click here and you have these two options, and naturally we're selecting the test bench because that's our top module. And then we'll click launch. So now the simulation is open. And you can see here you have the clock signal, you have the LED1, LED2, and we also have the constant clock period. So the last one here is there's nothing interesting happening here. That will stay on this value all the time. And if I scroll here, you can see that the clock is actually moving. It might be easier to see if I zoom out a little bit. You can see we have the clock signal. So the clock is running. You will also see that nothing is happening on LED1 and LED2, but that's because that this simulation is only run for a period of 1 microsecond. So because of the frequency of the blinking of the LEDs is in the vicinity of a half to a second or something, we of course need to run the simulation for a lot longer. And it takes some time, but you can do that. So what we do here is we'll set the simulation time for 1 second, then we will reset the simulation, and then we'll press run. So this will take some time, but I'll pause it and then we'll be back when it's done. So now the simulation is done, and it simulates an entire second run of this hardware. In order to get a bit more overview of what is happening, it's a good idea to zoom to full view. And now you can see that, well, the clock is, well, there's too much happening for you to see it here, but you can see that the LED1 and the LED2 is actually running, and you can find the timing of it. Also, if you're interested in the exact timing of when things are happening. Yeah, this were a introduction to how to do a behavioral simulation using iSim from within PlanAhead. Thank you for listening in. Bye bye.